Chapter 25 covers our galaxy, the Milky Way. The term Milky Way is actually used to mean two different but related things. Until 100 years ago, we didn't know for sure what a galaxy is or that we live inside one. But throughout history, people have seen this bright band of light with dark patches arching across the sky. It was referred to by different names in different places. The ancient Greeks called it the Milky Way. Around 400 years ago, Galileo first pointed a telescope at it and noticed that the fuzzy white band actually resolves into thousands of individual stars. And we've since learned that the dark patches are dusty clouds. In the near infrared, we can look through most of the dust and study the Milky Way in detail. This image was created by stitching together hundreds or thousands of images of the sky taken from two different locations on Earth. It's clear that the Milky Way includes a flat disk and a round central bulge. This image is actually a full 360-degree panorama. In other words, the right edge and left edge of this image show the same part of the sky, which is in the opposite direction as the center of this image. When we face away from the center of the galaxy, we still see some disk. This tells us that we live inside the disk, not right at the center, but also not all the way out at an edge. Now here is an image of another galaxy. This is what we call an edge-on spiral galaxy. We can see that it also has a disk with dusty clouds and a bright central bulge. Now that we've imaged millions of spiral galaxies, it's clear that we live inside one. Since we live in the disk of our galaxy, we can only view it edge-on. If we could fly tens of thousands of light years perpendicular to the disk, we'd be able to see the galaxy face-on. Perhaps it'll look like one of these galaxies. In the one at the left, the spiral arms appear to go nearly all the way to the center, where they disappear into the bulge. On the one at the right, as you trace the spiral arms from the outside in, they abruptly stop, and then there's a bar that connects them to the middle and to the other side. So spiral galaxies can be barred, like the one on the right, or unbarred, like the one on the left. In an edge-on galaxy, it's hard to see bars directly, but by studying our galaxy closely for the last 20 years or so, we've started to realize that the Milky Way most likely contains a bar. We think we actually live in a barred galaxy. By putting together everything we've observed about the Milky Way, we can construct a model of it. We think it has two obvious components, the disk and the bulge, and some not so obvious components, like a possible bar, and something called the halo. People that study the Milky Way have noticed that the disk consists of two different components called the thin disk and the thick disk, but you don't have to worry about that for this course. In visible light, the only things we see in the halo are dense clusters of stars called globular clusters. Those are the things that are shown as white circles in this model. With an X-ray telescope, we can see additional material in the halo. We see hot plumes of gas rising and falling from the disk. Here is a globular cluster. Each one can contain up to 1 million stars, and they're all old. All of the stars in the Milky Way's globular clusters are over 10 billion years old. So these globular clusters must have formed when the galaxy itself was forming over 10 billion years ago. Here's a model of our region of the Milky Way disk. We now think we live in a spur, which in this context means connector. We're in the Orion spur, which connects two of the main spiral arms. The arms and the spurs are named after the constellations where we can best see them. You don't have to remember the names. Stars in the disk all orbit the center of the galaxy in the same direction. The globular clusters in the halo also orbit the galactic center, but in random directions. So you could have one globular cluster moving in one direction, let's say clockwise, and another one right next to it moving in the opposite direction, counterclockwise. Globular clusters will pass through the disk as they orbit. The bulge is not shown in these two diagrams, but stars in the bulge have some randomness and some rotation to their motions. Their orbits are much less orderly than disk stars, but not completely random like the globular clusters. Now I'm going to describe one of the most challenging concepts in this course, and so I need you to pay close attention. You might remember that you can measure the mass of an object if it has something orbiting it, according to Newton's version of Kepler's third law. The size and speed of the orbit tells you the mass contained inside. Let's take the solar system. Here's the rotation curve for the solar system's planets plus Pluto. The rotation curve is a graph showing distance from the center on the x-axis and orbital speed or orbital velocity on the y-axis. You can see that Mercury orbits fast, Venus orbits slower, Earth even slower, etc. Each planet has to move at the right speed to stay in orbit. Like with many other systems, it's a balance between gravity and speed. If a planet doesn't move fast enough, gravity will win and the planet will spiral into the sun. If it moves too fast, it'll be released from orbit and escape from the solar system. Since the force of gravitation from the sun gets weaker as you move away from the sun, the further a planet is from the sun, the slower it has to move. The shape of a rotation curve tells you where the mass lies. In the case of the solar system, all of the mass is contained inside the orbit of Mercury. In other words, the sun pretty much contains all of the mass in the solar system. Living here on Earth, we might think of our planet as being huge, but it's tiny compared to the sun. In fact, even Jupiter is. If you put all of the planets and the moons and the asteroids and the comets together, it would amount to less than 1/10 of 1% of the solar system's mass. The sun contains over 99.9% of the mass of the solar system. Let's now apply what we've learned to the Milky Way galaxy. I'm going to show you the Milky Way's rotation curve, but first I'd like you to try to predict how it'll look. I'll pause for a couple of seconds and then give you my prediction based on how our galaxy appears to us. Here's a model of the galaxy again. One major difference between the solar system and the Milky Way is that most of the Milky Way's mass does not appear to lie right in the center. It is spread out. So if you imagine orbits of stars in the bulge, as you go from the inner bulge to the outer bulge, more and more mass will be contained inside of the orbits. More mass means more gravity. To withstand the gravity, stars have to move fast. So the rotation curve inside the bulge will not decrease like the solar system's rotation curve. It might be flat, or it might even increase. Then we get out into the disk, which appears to be less dense than the bulge. But still, we're adding mass. If I were forced to make a prediction, I might say the rotation curve should increase in the bulge and then flatten off in the disk. Once we're further out than the sun, I'd expect the rotation curve to eventually start decreasing because most of the galaxy's mass is now contained inside. So stars in the outer parts of the disk should be moving much slower than stars in the inner part. The rotation curve of the outer disk should look like the rotation curve for the solar system. Now here's the actual rotation curve of the galaxy. The distances shown are in kiloparsecs, or thousands of parsecs. We're around 8 kiloparsecs from the center. Again, a parsec is 3.26 light years. So 8 kiloparsecs is something like 25,000 light years. Let's see how good my prediction was. In the inner region, where the bulge is, I said the rotation curve should increase, and then it might flatten out as we leave the bulge and enter the disk. That is pretty much what we see. We see it rising from the center out into the bulge, and then it goes up and down. Maybe the spiral arms have something to do with that. And then eventually we would expect it to drop. That's what the blue curve shows. That's a prediction. Once we're twice as far out from the center of the galaxy as the sun is, you would expect the speeds to start going down. The actual curve is shown in red. Objects in the outer disk, 3, 4, 5 times as far out as we are, so 16, 24, 32 kiloparsecs away from the center, are moving just as fast as those in the inner parts, if not faster. At these speeds, they should have escaped from the galaxy, if the visible mass of the galaxy is the total mass of the galaxy. The gravity of the visible mass isn't nearly enough to hold the outer parts of the galaxy together. There must be lots of mass in the outer regions that we're not seeing. We call this dark matter. It's dark not just in the visible, but also in every other type of light, including radio, infrared, X-ray, etc. How much dark matter do we need to explain the galaxy's rotation curve? At least 10 times more dark matter than visible matter. At least 90% of the mass in the galaxy is made up of some stuff we've never seen directly. That's why we call it dark matter. We don't know what it is, but we can't explain the galaxy's rotation curve without it. We need it to exist for the rotation curve to make sense. This concludes part 1 of my lecture on the Milky Way.